scientists and engineers involved in nuclear weapons programs. Cyber espionage. Cyber espionage involves the use of computer networks and the Internet to gather information about nuclear weapons programs. This includes the use of malware and other cyber attacks to gain access to sensitive information. Implications of espionage and intelligence activities related to nuclear weapons programs. Espionage and intelligence activities related to nuclear weapons programs have significant implications for international security. The gathering of information about nuclear weapons programs can provide countries with valuable insights into the capabilities and intentions of their rivals. However, the use of espionage and intelligence activities can also lead to tensions and mistrust between countries. In some cases, espionage and intelligence activities related to nuclear weapons programs have led to major diplomatic incidents. For example, the 1960 U-2 incident led to a major deterioration in Soviet relations. Similarly, the revelation of Israel's nuclear weapons program by Mordechai Vanunu in 1986 led to a major diplomatic incident between Israel and the United States. Conclusion. In conclusion, espionage and intelligence activities related to nuclear weapons programs have been ongoing since the Cold War era. Countries engage in a range of methods to gather information about the nuclear weapons programs of their rivals, including technical collection, human intelligence, and cyber espionage. While the gathering of information can provide valuable insights into the capabilities and intentions of other countries, the use of espionage and intelligence activities can also lead to tensions and mistrust between countries. As the international community seeks to prevent the proliferation of nuclear weapons, the role of espionage and intelligence activities in gathering information about nuclear weapons programs will remain a significant issue. Current challenges and future directions of espionage and intelligence activities related to nuclear weapons programs. While espionage and intelligence activities related to nuclear weapons programs have a long history, there are still several challenges that need to be addressed. Here are some of the current challenges and future directions of espionage and intelligence activities related to nuclear weapons programs. Cybersecurity. The use of cyber espionage to gather information about nuclear weapons programs is becoming increasingly common. As a result, countries need to invest in cybersecurity measures to protect their sensitive information from cyber attacks. Emerging technologies. The development of emerging technologies, such as artificial intelligence and quantum computing, could significantly impact espionage and intelligence activities related to nuclear weapons programs. Future advancements in these technologies will likely play an important role in gathering and analyzing information about nuclear weapons programs. International cooperation. International cooperation is essential to preventing the proliferation of nuclear weapons. Countries need to work together to share information about nuclear weapons programs and to prevent the spread of nuclear technology and materials to non-state actors. Ethical considerations. The use of espionage and intelligence activities to gather information about nuclear weapons programs raises ethical considerations. Countries need to consider the potential consequences of their actions and ensure that they are acting in accordance with international law and norms. Future directions of espionage and intelligence activities related to nuclear weapons programs. As the international community seeks to prevent the proliferation of nuclear weapons, future advancements in espionage and intelligence activities related to nuclear weapons programs will focus on developing new methods and technologies to gather and analyze information. Here are some potential future directions of espionage and intelligence activities related to nuclear weapons programs. Quantum computing. the development of quantum computing could significantly impact espionage and intelligence activities related to nuclear weapons programs by providing new methods for analyzing and interpreting data. Biometric identification. Biometric identification technologies, such as facial recognition and fingerprint analysis, could be used to identify individuals involved in nuclear weapons programs. Social media analysis. The analysis of social media data could be used to gather information about the activities of individuals involved in nuclear weapons programs. International standards. The development of international standards for the use of espionage and intelligence activities related to nuclear weapons programs could help to ensure that countries are acting in accordance with international law and norms. Conclusion. In conclusion, espionage and intelligence activities related to nuclear weapons programs have a long history and continue to be a significant issue for the international community. While there are still challenges to be addressed, future advancements in espionage and intelligence activities will likely play an important role in preventing the proliferation of nuclear weapons. By recognizing the importance of espionage and intelligence activities related to applications of chemistry in the production and use of plastics and fibers. Plastics and fibers are ubiquitous in modern society, with a wide range of applications in fields such as packaging, construction, and textiles. The production and use of plastics and fibers rely heavily on chemistry, with chemical processes and materials playing a crucial role in their development and optimization. In this article, we will explore the applications of chemistry in the production and use of plastics and fibers. Chemistry in the production of plastics. The production of plastics involves a range of chemical processes and materials, with each step playing a crucial role in the final product. Here are some examples of the applications of chemistry in the production of plastics. Monomer synthesis. Plastics are typically made from small molecules called monomers, which are chemically bonded to form polymers. The synthesis of monomers involves various chemical reactions, such as polymerization and condensation reactions. Polymerization. Polymerization is a chemical process in which monomers are chemically bonded to form long chains of polymers. Different types of polymerization reactions are used to produce different types of plastics, such as addition polymerization and condensation polymerization. Catalysts. Catalysts are used in the production of plastics to speed up chemical reactions and to control the properties of the final product. Different types of catalysts are used for different types of plastics, such as Ziegler-Natta catalysts for polyethylene production. Additives. Additives are used to modify the properties of plastics, such as their strength, flexibility, and color. Examples of additives used in plastics production include plasticizers, stabilizers, and pigments. Chemistry in the use of plastics. The use of plastics also relies heavily on chemistry, with chemical processes and materials playing a crucial role in their optimization and modification. Here are some examples of the applications of chemistry in the use of plastics. Polymer modification. Polymer modification involves the use of various chemical processes to modify the properties of plastics, such as their strength, flexibility, and heat resistance. Examples of polymer modification processes include cross-linking, grafting, and blending. Recycling. Recycling is an important application of chemistry in the use of plastics. Chemical processes such as pyrolysis and depolymerization are used to break down plastics into their constituent monomers, which can then be used to produce new plastics. Additives. Additives are also used in the use of plastics to modify their properties. Examples of additives used in the use of plastics include flame retardants, UV stabilizers, and antimicrobial agents. Chemistry in the production of fibers. The production of fibers also involves a range of chemical processes and materials, with each step playing a crucial role in the final product. Here are some examples of the applications of chemistry in the production of fibers. Polymer synthesis. Fibers are typically made from polymers, which are chemically bonded to form long chains. The synthesis of polymers involves various chemical reactions, such as polymerization and condensation reactions. Spinning. Spinning is a process in which polymers are extruded through a spinneret to form fibers. Different spinning processes are used to produce different types of fibers, such as melt spinning and dry spinning. Cross-linking. Cross-linking is a chemical process used to modify the properties of fibers, such as their strength and resistance to heat and chemicals. Examples of cross-linking processes used in fiber production include radiation cross-linking and chemical cross-linking. Additives. Additives are also used in the production of fibers to modify their properties. Examples of additives used in fiber production include flame retardants, UV stabilizers, and antimicrobial agents. Chemistry in the use of fibers. The use of fibers also relies heavily on chemistry, with chemical processes and materials playing a crucial role in their optimization and modification. Here are some examples of the applications of chemistry in the use of fibers. Polymer modification. Polymer modification involves the use of various chemical processes to modify the properties of fibers, such as their strength, flexibility, and resistance to heat and chemicals. Examples of polymer modification processes include cross-linking, grafting, and blending. Fabrication. Fabrication is a process in which fibers are woven or knitted to form textiles. Different types of fabrication processes are used to produce different types of textiles, such as weaving and circular knitting. Dyeing and printing. Dyeing and printing are processes used to color fibers and textiles. These processes involve the use of various chemical compounds, such as dyes and pigments. Recycling. Recycling is an important application of chemistry in the use of fibers. Chemical processes such as pyrolysis and depolymerization are used to break down fibers into their constituent monomers, which can then be used to produce new fibers. Conclusion. In conclusion, the production and use of plastics and fibers rely heavily on chemistry, with chemical processes and materials playing a crucial role in their development and optimization. From the synthesis of monomers to the modification of polymers and the fabrication of textiles, chemistry plays a central role in the production and use of plastics and fibers. By recognizing the importance of chemistry in these fields, we can better appreciate the scientific advancements that have made these materials so ubiquitous in modern society. Current challenges and future directions of chemistry in the production and use of plastics and fibers. While chemistry has played a crucial role in the production and use of plastics and fibers, there are still several challenges that need to be addressed. Here are some of the current challenges and future directions of chemistry in the production and use of plastics and fibers. Environmental impact. Plastics and fibers have a significant environmental impact, with issues such as plastic pollution and microplastics being major concerns. Chemistry can play a crucial role in developing more sustainable materials and processes that reduce the environmental impact of plastics and fibers. Circular economy. The circular economy is an emerging concept that aims to promote the reuse and recycling of materials to reduce waste and promote sustainability. Chemistry can play a central role in developing new materials and processes that are compatible with the circular economy. Emerging technologies. Emerging technologies, such as nanotechnology and biotechnology, could significantly impact the production and use of plastics and fibers. Future advancements in these technologies will likely play an important role in developing new materials and processes for the production and use of plastics and fibers. Energy efficiency. The production of plastics and fibers is energy intensive, with significant amounts of energy required to synthesize polymers and to manufacture textiles. Chemistry can play a crucial role in developing more energy-efficient processes and materials that reduce the energy consumption of plastics and fibers production. Future directions of chemistry in the production and use of plastics and fibers. As the world seeks to reduce the environmental impact of plastics and fibers, future advancements in chemistry will focus on developing new materials and processes that are more sustainable and compatible with a circular economy. Here are some potential future directions of chemistry in the production and use of plastics and fibers. Bioplastics. Bioplastics are plastics that are made from renewable resources, such as plant-based materials. Organic compounds have become an important part of modern agriculture, as they have been widely used in the manufacturing and application of various plant protection products, including pesticides and fungicides. These compounds have contributed significantly to the improvement of agricultural productivity and the control of pests and diseases, ultimately ensuring food security for the growing population. Organic compounds are compounds that contain carbon atoms, and they are found in a wide variety of natural and synthetic products. The use of organic compounds in agriculture dates back to ancient times, when natural products such as garlic, tobacco, and neem were used to control pests and diseases. In modern times, synthetic organic compounds have been developed to provide more effective and targeted control of pests and diseases. One of the most common applications of organic compounds in agriculture is in the production of pesticides. Pesticides are chemicals that are used to control pests, including insects, weeds, and fungi. These chemicals can be used to protect crops from damage caused by pests, ultimately increasing yields and improving crop quality. There are several types of organic compounds used in the production of pesticides. One example is organophosphates, which are used to control a wide range of pests, including insects and mites. These compounds work by interfering with the nervous system of pests, ultimately causing paralysis and death. Another example is pyrethroids, which are similar in structure to natural compounds found in chrysanthemums. Pyrethroids are used to control a range of pests, including insects and mites, and they work by paralyzing the pest's nervous system. In addition to pesticides, organic compounds are also used in the production of fungicides. Fungicides are chemicals that are used to control fungal diseases, which can cause significant damage to crops. These chemicals can be used to protect crops from diseases such as powdery mildew, rust, and blight, ultimately improving crop yields and quality. There are several types of organic compounds used in the production of fungicides. One example is triazoles, which are used to control a wide range of fungal diseases. Triazoles work by inhibiting the production of ergosterol, which is an essential component of fungal cell membranes. Another example is strobilurins, which are used to control a range of fungal diseases, including powdery mildew and rust. Strobilurins work by interfering with the energy production of fungi, ultimately causing the fungi to die. Despite the many advantages of organic compounds in agriculture, there are also concerns about their potential impact on human health and the environment. For example, some organic compounds have been linked to adverse health effects, including cancer and reproductive problems. There are also concerns about the environmental impact of these compounds, particularly when they are used in large quantities or when they are not disposed of properly. To address these concerns, researchers and industry leaders are exploring new ways to reduce the environmental and health impacts of organic compounds in agriculture. For example, there is growing interest in the development of more targeted and less toxic pesticides and fungicides. There is also interest in the development of new production methods that use fewer chemicals or generate less waste. In addition, there is growing interest in the use of natural products and biological control methods as alternatives to synthetic organic compounds. These methods involve the use of natural products such as plant extracts and microorganisms to control pests and diseases, ultimately reducing the need for synthetic chemicals. In conclusion, organic compounds have become an important part of modern agriculture, and their use has contributed significantly to the improvement of agricultural productivity and the control of pests and diseases. However, it is important to consider the potential impact of these compounds on human health and the environment, and to work towards more sustainable and responsible solutions. By doing so, we can continue to harness the benefits of organic compounds in agriculture while minimizing their negative impact on our health and the environment. One of the challenges associated with the use of organic compounds in agriculture is the development of resistance in pests and diseases. Pests and diseases can evolve and adapt to the use of pesticides and fungicides, ultimately reducing the effectiveness of these compounds. This can lead to the need for higher doses of chemicals or the use of more toxic compounds, which can have negative impacts on human health and the environment. To address this challenge, researchers and industry leaders are exploring new approaches to pest and disease control that are less reliant on synthetic chemicals. One approach is the use of integrated pest management, IPM, which involves the use of a combination of techniques, including cultural, biological, and chemical controls. This approach can reduce the reliance on synthetic chemicals and promote more sustainable and effective pest and disease control. Another approach is the use of genetic engineering to produce crops that are resistant to pests and diseases. This approach involves the insertion of genes into crops that produce proteins that are toxic to pests or that activate the plant's natural defense mechanisms. This approach can reduce the need for synthetic chemicals and promote more sustainable and effective pest and disease control. In addition, there is growing interest in the use of precision agriculture technologies to improve the efficiency and effectiveness of crop protection. Precision agriculture involves the use of sensors and other technologies to collect data on crop health and environmental conditions, ultimately allowing for more targeted and efficient application of pesticides and fungicides. Despite the challenges associated with the use of organic compounds in agriculture, their many advantages have made them a vital component of modern agriculture. Ongoing research and development are likely to uncover new uses and applications for these compounds. And it is important to continue exploring ways to harness the benefits of organic compounds in agriculture while minimizing their negative impact on our health and the environment. Another challenge associated with the use of organic compounds in agriculture is the potential for these compounds to contaminate soil, water, and air. Pesticides and fungicides can enter the environment through runoff, leaching, and volatilization, ultimately affecting the quality of soil, water, and air. This can have negative impacts on human health and the environment, including the loss of biodiversity and the degradation of ecosystems. To address this challenge, researchers and industry leaders are exploring new ways to reduce the environmental impact of organic compounds in agriculture. For example, there is growing interest in the development of new formulations and application methods that can reduce the amount of chemicals that are released into the environment. There is also interest in the development of new monitoring and assessment methods that can detect and quantify the presence of organic compounds in the environment. In addition, there is growing interest in the use of organic farming practices as an alternative to conventional agriculture. Organic farming involves the use of natural products and methods to control pests and diseases, ultimately reducing the reliance on synthetic chemicals. Organic farming also promotes the use of sustainable production methods and the conservation of biodiversity, ultimately promoting more sustainable and responsible agriculture. The use of organic compounds in agriculture is a complex issue that requires careful consideration of the potential benefits and risks. While these compounds have contributed significantly to the improvement of agricultural technology has revolutionized the way we live our lives. From the way we communicate to the way we work, technology has changed everything. One area where technology has made a significant impact is in the development of elastic materials like rubber and elastomers. These materials have been used in a wide range of products, from tires to medical devices, and have played a key role in driving innovation and progress in various industries. Elastomers are a class of materials that exhibit elastic properties, meaning they can be stretched and then returned to their original shape. They are typically made from synthetic rubbers such as polyurethane, silicone, and polybutadiene. These materials are used in a variety of applications due to their unique properties, including their ability to withstand high stress, resist abrasion, and provide excellent sealing capabilities. One of the most common uses of elastomers is in the production of tires. The rubber used in tires is a type of elastomer that is specifically designed to withstand the high stress and wear and tear of the road. The use of elastomers in tires has greatly improved their durability and performance, allowing for safer and more efficient transportation. Another area where elastomers have made a significant impact is in the medical industry. Elastomers are used in a range of medical devices, including catheters, implants, and prosthetics. These materials are ideal for these applications because they are biocompatible, meaning they do not cause an adverse reaction when introduced to the human body. Additionally, elastomers are flexible and can be shaped to fit specific applications, making them ideal for complex medical procedures. Elastomers are also used in the production of consumer goods such as clothing and footwear. For example, elastomers are used in the production of sports clothing and shoes to provide a comfortable, stretchy fit that allows for a full range of motion. Elastomers are also used in the production of swimwear, where their ability to withstand exposure to water and chlorine is essential. In recent years, there has been growing interest in the development of new types of elastomers that can be used in a wider range of applications. Researchers are exploring the use of nanoscale elastomers, which are tiny particles that can be incorporated into other materials to provide new properties. For example, nanoscale elastomers could be used to create materials that are self-healing, meaning they can repair themselves when damaged. Despite their many advantages, elastomers do have some limitations. For example, they can degrade over time when exposed to heat, light, and other environmental factors. Additionally, some elastomers are not suitable for use in high-temperature applications, as they can melt or break down at high temperatures. In conclusion, elastomers have had a significant impact on various industries, from transportation to healthcare. Their unique properties have made them ideal for a wide range of applications, and ongoing research is likely to uncover new uses for these versatile materials. As technology continues to evolve, we can expect to see even more innovative uses of elastomers in the future. One area where elastomers are expected to have a significant impact in the future is in the field of robotics. Elastomers can be used to create soft robotics, which are robots made from soft, flexible materials that can bend and stretch like human muscles. Soft robotics have the potential to revolutionize a wide range of applications, from medical devices to search and rescue operations. Another area where elastomers are expected to have a significant impact is in the development of smart materials. Smart materials are materials that can change their properties in response to external stimuli, such as temperature or pressure. Elastomers can be used to create smart materials that can change their shape or stiffness in response to changes in temperature or other environmental factors. This could lead to the development of new products with unique properties, such as clothing that can automatically adjust to changes in temperature. In addition to their use in products, elastomers also have environmental benefits. For example, the use of elastomers in tires has helped to reduce the amount of waste generated by the tire industry. Elastomers are also used in the production of sustainable materials, such as recycled rubber, which can be used in a wide range of applications. Despite their many advantages, there are also challenges associated with the use of elastomers. For example, the production of some elastomers can be energy-intensive and involve the use of hazardous chemicals. There are also concerns about the environmental impact of elastomers, particularly when they are disposed of at the end of their useful life. To address these challenges, researchers and industry leaders are exploring new manufacturing processes and materials that can reduce the environmental impact of elastomers. For example, there is growing interest in the use of biodegradable elastomers, which can break down naturally over time and reduce the amount of waste generated. In conclusion, elastomers have had a significant impact on various industries and have played a key role in driving innovation and progress. As technology continues to advance, we can expect to see even more innovative uses of elastomers in the future. However, it is important to consider the environmental impacts of these materials and work towards more sustainable solutions. By doing so, we can continue to harness the many benefits of elastomers while minimizing their environmental footprint. Another challenge associated with elastomers is their potential impact on human health. Some elastomers contain chemicals that can be harmful if they come into contact with the skin or are ingested. For example, some types of synthetic rubber contain chemicals called phthalates, which have been linked to reproductive and developmental problems in animals. While the risk to human health is still being studied, there is growing concern about the potential health effects of exposure to these chemicals. To address these concerns, researchers and industry leaders are exploring new materials and manufacturing processes that can reduce the use of harmful chemicals in elastomers. For example, there is growing interest in the use of natural rubber, which is derived from the sap of rubber trees and does not contain harmful chemicals. There is also interest in developing new manufacturing processes that use fewer chemicals or eliminate them altogether. Despite the challenges associated with elastomers, their many advantages have made them a vital component of our modern world. From tires to medical devices, elastomers have played a key role in driving innovation and progress in various industries. Ongoing research and development are likely to uncover new uses and applications for these versatile materials. And it is important to continue exploring ways to harness the benefits of elastomers while minimizing their environmental and health impacts. One area where elastomers are expected to make a significant impact in the future is in the field of wearable technology. Elastomers can be used to create flexible and stretchable electronics, which can be incorporated into clothing, accessories, and even the human body. This could lead to the development of new products with unique properties, such as clothing that can monitor vital signs or accessories that can be used to control electronic devices. Another area where elastomers are expected to have a significant impact is in the development of energy-efficient materials. Construction technology has come a long way in recent years, with advancements in materials and techniques that have improved both the efficiency and sustainability of construction projects. One area where technology has had a significant impact is in the development of adhesives and coatings for construction materials. In this article, we will explore the use of adhesives and coatings in construction, including the different types of products available and their benefits and challenges. Adhesives in construction. Adhesives are used in construction to bond a wide range of materials, including wood, metal, plastic, and concrete. Adhesives can provide a stronger and more durable bond than traditional mechanical fasteners such as nails and screws, and can also reduce the need for drilling and other invasive techniques that can weaken the structural integrity of materials. There are several types of adhesives used in construction, including epoxy adhesives. Epoxy adhesives are two-part adhesives that consist of a resin and a hardener. The two components are mixed together and applied to the materials to be bonded. Epoxy adhesives provide a strong and durable bond, and can be used in a wide range of temperatures and conditions. Polyurethane adhesives. Polyurethane adhesives are one-part adhesives that cure through a chemical reaction with moisture in the air. Polyurethane adhesives are flexible and can be used to bond materials with different coefficients of expansion. Cyanoacrylate adhesives. Cyanoacrylate adhesives, also known as superglues, are fast-drying adhesives that can bond a wide range of materials. Cyanoacrylate adhesives are often used for small repairs and in applications where a strong and fast bond is needed. Coatings in construction. Coatings are used in construction to protect and enhance the appearance of materials such as concrete, metal, and wood. Coatings can provide a barrier against moisture, UV radiation, and other environmental factors that can damage materials over time. Coatings can also be used to improve the appearance of materials, including adding color and texture. There are several types of coatings used in construction, including paints. Paints are the most common type of coating used in construction. Paints can be applied to a wide range of materials, including wood, metal, and concrete. Paints can provide both protection and aesthetic enhancement, and are available in a wide range of colors and finishes. Sealers. Sealers are used to protect concrete and other porous materials from moisture and other environmental factors. Sealers can also be used to enhance the appearance of materials, including adding a glossy or matte finish. Powder coatings. Powder coatings are a type of coating that is applied as a dry powder and then cured through a heating process. Powder coatings are often used to provide a durable and long-lasting finish for metal materials, including aluminum and steel. Benefits and challenges of adhesives and coatings in construction. The use of adhesives and coatings in construction can provide a wide range of benefits, including improved durability. Adhesives and coatings can provide a stronger and more durable bond or finish than traditional mechanical fasteners or surface treatments. Enhanced aesthetics. Adhesives and coatings can be used to improve the appearance of materials, including adding color, texture, and gloss. Greater efficiency. Adhesives and coatings can reduce the need for invasive techniques such as drilling and welding, saving time and reducing costs. However, there are also challenges associated with the use of adhesives and coatings in construction, including environmental concerns. Some adhesives and coatings contain volatile organic compounds, VOCs, and other hazardous chemicals that can be harmful to human health and the environment. Compatibility issues. Adhesives and coatings must be carefully selected to ensure compatibility with the materials being bonded or coated, and improper selection can lead to failure or damage. Adhesion issues. Adhesives and coatings can be affected by factors such as temperature, humidity, and surface preparation, and failure to properly address these factors can lead to poor adhesion or coating failure. Conclusion. Adhesives and coatings are essential components of modern construction, providing improved durability, aesthetics, and efficiency. However, the use of these products also presents challenges related to environmental concerns, compatibility, and adhesion. By carefully selecting and using adhesives and coatings that meet the needs of specific applications, construction professionals can ensure that their projects are both effective and sustainable. To address the challenges associated with the use of adhesives and coatings in construction, there have been significant advancements in the development of more sustainable and environmentally friendly products. For example, there are now low-VOC adhesives and coatings that minimize the release of harmful chemicals into the environment. Additionally, there are bio-based adhesives and coatings that are made from renewable resources such as soybeans and corn. Furthermore, there have been advancements in the use of nanotechnology in the development of adhesives and coatings. Nanotechnology involves the manipulation of materials at the nanoscale, which can lead to improvements in strength, durability, and other properties. For example, nano-sized particles can be added to adhesives and coatings to improve their resistance to UV radiation and other environmental factors. In addition to advancements in product development, there has also been an increased focus on the proper disposal of adhesives and coatings. Many of these products are considered hazardous waste and must be disposed of according to local regulations. Proper disposal can help to minimize the release of harmful chemicals into the environment and protect the health and safety of workers and the general public. In conclusion, adhesives and coatings are essential components of modern construction, providing improved durability, aesthetics, and efficiency. However, the use of these products presents challenges related to environmental concerns, compatibility, and adhesion. By carefully selecting and using adhesives and coatings that meet the needs of specific applications, construction professionals can ensure that their projects are both effective and sustainable. Advancements in product development and proper disposal practices can help to address the challenges associated with these products and promote a more sustainable approach to construction. Furthermore, The use of adhesives and coatings in construction is not limited to traditional construction materials such as wood, metal, and concrete. Advances in technology have led to the development of adhesives and coatings that can bond or coat a wide range of materials, including plastics, composites, and even living tissues. For example, medical adhesives are used to close wounds and incisions, and can provide a stronger and more flexible bond than traditional sutures or staples. Similarly, adhesives and coatings are used in the aerospace and automotive industries to bond or coat lightweight materials such as carbon fiber and aluminum. The use of adhesives and coatings in these industries presents unique challenges related to factors such as temperature, vibration, and impact resistance. However, advancements in product development have led to the development of specialized adhesives and coatings that can meet these challenges and provide a reliable and durable bond or coating. One example of a specialized adhesive is the structural adhesive used in aircraft construction. These adhesives must be able to bond high-strength materials such as aluminum and titanium, and must also be able to withstand temperature changes and vibrations during flight. Similarly, the coatings used on automotive parts must be able to protect against rust and corrosion, as well as withstand exposure to UV radiation and other environmental factors. In addition to their technical benefits, the use of adhesives and coatings in these industries can also provide Technology has had a profound impact on the textile industry, particularly in the development and use of synthetic and cellulose fibers. These fibers have revolutionized the way we produce textiles, allowing for increased efficiency, durability, and versatility. In this article, we will explore the different types of synthetic and cellulose fibers used in textile production, their properties, and their applications. Synthetic fibers. Synthetic fibers are made from petrochemicals and are manufactured through a process of polymerization. They are designed to mimic the properties of natural fibers such as silk, wool, and cotton, but with improved durability and strength. The most common types of synthetic fibers used in textile production include nylon, polyester, and acrylic. Nylon. Nylon was first introduced in the 1930s and quickly became popular due to its strength, durability, and elasticity. It is commonly used in the production of hosiery, swimwear, and lingerie, as well as in the automotive and aerospace industries. Nylon is also resistant to mold and mildew, making it ideal for outdoor applications. Polyester. Polyester is a synthetic fiber that is widely used in the textile industry due to its versatility and durability. It is resistant to wrinkles, shrinking, and stretching, making it ideal for use in clothing, bedding, and upholstery. Polyester is also lightweight and dries quickly, making it a popular choice for sportswear and outdoor gear. Acrylic. Acrylic is a synthetic fiber that is similar in texture to wool. It is commonly used in the production of blankets, sweaters, and scarves due to its warmth and softness. Acrylic is also resistant to sunlight and fading, making it ideal for outdoor applications. Cellulose fibers. Cellulose fibers are made from plant materials such as cotton, linen, and bamboo. They are biodegradable and renewable, making them a more environmentally friendly alternative to synthetic fibers. The most common types of cellulose fibers used in textile production include cotton, rayon, and bamboo. Cotton. Cotton is a natural fiber that has been used for thousands of years in textile production. It is breathable, soft, and comfortable, making it ideal for use in clothing and bedding. Cotton is also absorbent and easy to care for, making it a popular choice for everyday wear. Rayon. Rayon is a cellulose fiber that is made from wood pulp. It is soft, lightweight, and breathable, making it ideal for use in clothing and home furnishings. Rayon is also moisture absorbent, making it a popular choice for summer clothing. Bamboo. Bamboo is a fast-growing plant that is used to produce a soft and durable cellulose fiber. It is a sustainable alternative to other types of cellulose fibers and is biodegradable. Bamboo is also naturally moisture-wicking and hypoallergenic, making it a popular choice for activewear and undergarments. Applications of synthetic and cellulose fibers. The development of synthetic and cellulose fibers has had a significant impact on the textile industry, allowing for increased efficiency and versatility in textile production. Synthetic fibers are often used in the production of sportswear, outdoor gear, and automotive and aerospace applications, while cellulose fibers are more commonly used in clothing and home furnishings. The use of synthetic and cellulose fibers has also led to the development of new and innovative textile products. For example, the use of nylon in the production of hosiery has led to the development of compression socks, which are designed to improve blood flow and reduce swelling. The use of polyester in bedding has led to the development of microfiber sheets, which are lightweight, durable, and easy to care for. The use of bamboo in activewear has led to the development of moisture-wicking and hypoallergenic clothing, which is ideal for people with sensitive skin. Conclusion. In conclusion, the development and use of synthetic and cellulose fibers has had a significant impact on the textile industry. These fibers have allowed for increased efficiency, durability, and versatility in textile production, leading to the development of new and innovative textile products. The use of synthetic and cellulose fibers has also led to a more sustainable approach to textile production, with the development of biodegradable and renewable fibers such as bamboo and cotton. As technology continues to advance, it is likely that we will see further innovations in textile production. With new and improved synthetic and cellulose fibers being developed and used in a wide range of applications. Advancements in technology have also led to the development of new processes for producing synthetic and cellulose fibers. For example, electrospinning is a technique that is used to produce ultrafine fibers that are strong and durable. This process involves the use of an electrical charge to draw a liquid polymer through a small nozzle, creating a fiber that is thinner than a human hair. These ultrafine fibers have a wide range of applications, including in medical devices, filtration systems, and protective clothing. Another emerging technology in the textile industry is 3D printing. 3D printing involves the layer-by-layer construction of a three-dimensional object using a digital model. This technology has the potential to revolutionize textile production, allowing for the creation of complex and intricate designs with minimal waste. It also has the potential to allow for on-demand production, reducing the need for large-scale manufacturing facilities and transportation. However, despite the many benefits of synthetic and cellulose fibers, there are also concerns about their environmental impact. Synthetic fibers are made from non-renewable resources and can take hundreds of years to biodegrade, leading to pollution and waste. Cellulose fibers, while more sustainable, still require significant amounts of water and energy to produce. Additionally, the use of pesticides and other chemicals in cotton production can have negative environmental impacts. To address these concerns, there is a growing interest in sustainable and eco-friendly textiles. This includes the use of recycled materials, such as recycled polyester and cotton, as well as the development of new fibers made from renewable resources such as algae and mushrooms. There is also a growing interest in production processes that minimize waste and reduce the environmental impact of textile production. In conclusion, the use of synthetic and cellulose fibers has had a profound impact on the textile industry, allowing for increased efficiency, durability, and versatility. These fibers have led to the development of new and innovative textile products, as well as advancements in production processes such as electrospinning and 3D printing. However, there are also concerns about the environmental impact of these fibers, leading to a growing interest in sustainable and eco-friendly textiles. As technology continues to advance, it is likely that we will see further innovations in textile production, with a continued focus on sustainability and reducing environmental impact. One area of particular focus in sustainable textile production is the development of circular economy models. Chemistry plays a critical role in a wide range of applications, including those related to intelligence and surveillance in military and security operations. From the development of new materials for protective gear to the analysis of chemical signatures in explosives and other materials, chemistry is a vital component of modern military and security operations. In this article, we will explore some of the key applications of chemistry in intelligence and surveillance, as well as the challenges and opportunities associated with these applications. Chemical sensors and detection technologies. Chemical sensors and detection technologies are critical tools for intelligence and surveillance operations. These technologies can be used to detect and identify a wide range of chemical compounds, including explosives, drugs, and chemical weapons. Chemical sensors can be deployed in a variety of settings, including airports, border checkpoints, and military installations, and can provide rapid and accurate detection of chemical threats. One example of a chemical sensor technology is the Ion Mobility Spectrometer, IMS, which is used to detect trace amounts of chemicals in the air. IMS can be used to detect a wide range of chemical compounds, including explosive materials and drugs, and can provide real-time detection in a variety of settings. Another example is the use of gas chromatography mass spectrometry, GCMS, for the analysis of chemical signatures in explosives and other materials. Chemical protective gear. Chemical protective gear is another critical application of chemistry in military and security operations. Chemical protective gear is designed to protect military personnel and first responders from exposure to a wide range of hazardous chemicals, including chemical weapons and toxic industrial chemicals. Chemical protective gear can include respirators, protective clothing, and other equipment designed to prevent exposure to chemical agents. The development of new materials for chemical protective gear is an ongoing area of research. With a focus on improving the effectiveness and comfort of protective gear while reducing the weight and bulk of the equipment. For example, researchers are exploring the use of nanomaterials and other advanced materials in the development of new chemical protective gear that is more effective and more comfortable to wear. Chemical forensics. Chemical forensics is another important application of chemistry in intelligence and surveillance. Chemical forensics involves the analysis of chemical signatures in materials to identify their origin and composition. This can include the analysis of explosives, drugs, and other materials used in criminal and terrorist activities. Chemical forensics can provide critical information for intelligence and surveillance operations, including the identification of suspects and the tracing of materials back to their source. Chemical forensic techniques can include mass spectrometry, gas chromatography, and other analytical techniques that can provide detailed information about the chemical composition of materials. Challenges and opportunities. While the applications of chemistry in intelligence and surveillance are numerous, there are also challenges and opportunities associated with these applications. One challenge is the potential for false positives or false negatives in chemical detection technologies, which can lead to inaccurate or incomplete information for intelligence and surveillance operations. Another challenge is the need for continuous research and development to stay ahead of new and emerging chemical threats. At the same time, there are also opportunities to improve the effectiveness and efficiency of intelligence and surveillance operations through the use of chemistry. New materials and technologies can provide better protection for military personnel and first responders, while new analytical techniques can provide more detailed information about chemical threats and their sources. Conclusion: chemistry plays a critical role in intelligence and surveillance operations in military and security contexts. From the development of new materials for protective gear to the analysis of chemical signatures in explosives and other materials, chemistry is a vital component of modern military and security operations. While there are challenges associated with the use of chemistry in intelligence and surveillance, there are also opportunities to improve the effectiveness and efficiency of these operations through ongoing research and development. As such, chemistry will continue to be an important tool for intelligence and surveillance in military and security contexts in the years to come. Chemical sensing and detection technologies, chemical protective gear, and chemical forensics are just a few of the key applications of chemistry in intelligence and surveillance operations. However, there are many other areas where chemistry can play a critical role in military and security contexts. For example, chemistry can be used in the development of new materials for electronics and sensors, which can provide enhanced capabilities for intelligence gathering and surveillance. Chemistry can also be used in the development of new materials for energy storage and conversion, which can provide better power sources for military operations. Another area where chemistry is playing an increasingly important role is in the development of new drugs and vaccines for infectious diseases. In military and security contexts, infectious diseases can pose a serious threat to personnel and can be used as a weapon by hostile actors. Chemistry is a critical tool in the development of new drugs and vaccines that can protect military personnel and first responders from these threats. In addition, chemistry can be used in the development of new materials for water purification and desalination, which can provide better access to clean water in military and security contexts. Water scarcity can be a major challenge in many parts of the world, and providing access to clean water is critical for the health and well-being of military personnel and local populations. As we move forward, it is clear that chemistry will continue to play a critical role in intelligence and surveillance operations in military and security contexts. By continuing to innovate and develop new materials, technologies, and analytical techniques, we can improve the effectiveness and efficiency of these operations and better protect military personnel and first responders from chemical threats. However, it is also important to consider the ethical and societal implications of the use of chemistry in military and security contexts. Chemical weapons, for example, are banned under international law due to their indiscriminate and devastating effects on both combatants and civilians. The use of chemical sensing and detection technologies, while critical for intelligence and surveillance operations, must also be balanced with the need to protect individual privacy and civil liberties. Additionally, the development of new materials and technologies for military and security contexts can have unintended consequences for the environment and public health. It is important to consider the potential environmental and health impacts of these materials and technologies, and to work to minimize any negative effects. Finally, it is important to recognize that chemistry is just one component of a larger system of intelligence and surveillance operations in military and security contexts. To truly address the challenges facing these operations, we must also consider issues such as transparency, accountability, and respect for human rights. By taking a holistic approach to intelligence and surveillance operations, we can create a more effective and responsible system that benefits all stakeholders. In conclusion, chemistry plays a critical role in intelligence and surveillance operations in military and security contexts. From chemical sensing and detection technologies to chemical protective gear and chemical forensics, chemistry is a vital tool for protecting military personnel and first responders from chemical threats. However, it is important to consider the ethical and societal implications of the use of chemistry in these contexts, and to work to minimize any negative impacts on the environment and public health. By doing so, we can create a more effective and responsible system of intelligence and surveillance operations that benefits all stakeholders.